Okay, welcome back, everybody. So we're moving on to section 19.3, which talks about the Dirac delta function. And actually, to be fair about where we're headed here in the Dirac delta function section and some future sections, we have to jump back to the previous lecture where I mentioned really quick that the Fourier transform, as a series becomes an integral as L goes to infinity. And actually that's the Fourier transform over the interval minus L to L, which means my inner product with f with e to the I 2 pi k x over L, which traditionally would look something like this, f of x e to the minus I 2 pi k x over L dx. If I end up taking L to infinity right there, right there, right there, and right there, then what I get is 1 divided by root 2 pi integral minus infinity to infinity f of x e to the minus I 2 pi kx dx. And actually, I'm thinking about this a little more right now. That's not there if I included 2 pi in the exponential there. So I recover this integral as the inner product. So that integral is the inner product, and actually to reconstruct f of x from its transform, f hat, so this is the inner product, which is also known as the transform, f hat of k. To reconstruct f of x from f hat of k, we have, instead of my series, I actually repeat this procedure. Now I have a 1 over 2 pi out to infinity, f of x, f hat, do not. Actually, an integral minus infinity to infinity, f hat of k e to the I 2 pi k x dk. So the integral is taken over the k variable. And so this is your inverse, Fourier inverse on f hat, and this is your Fourier transform on f. Maybe I'll circle those just so we're a little bit more clear about how this looks in the L going to infinity section. So just kind of maybe pause your screen there and keep an eye on what that looks like. But this is useful because when we jump back now to the Dirac delta function, we start to utilize some very important properties of these integral transforms instead. So the Dirac delta function, now I'm going to put that square around the word function because it's a generalized function. Okay, so that's something that's really important to note. This is not a traditional mathematical function. This does not exist as a regular function, what we would normally use the term function as. It's its own special function, which we call generalized functions. But it has the property that if I integrate any function against the Dirac delta function, okay, so this looks like an inner product, right? So this is the inner product of f with delta. What I get out of that is f at 0, evaluation of f at 0. And if the interval, all we have to do is integrate over an interval which contains 0, and this is still true. Now what's useful is this notion of saying, okay, maybe I'm going to shift the delta function then. If I shift the delta function to some point, then under a really easy change of variables, you would see pretty quickly that means you should evaluate at x0. So this is just something that we're going to get used to today, right? There's the remark saying that it's not actually a function. I'm not going to talk about the next part. That's not very important. So something that's useful, though, is that you can define it using the integral version of the Fourier transform. The delta function here is the Fourier transform in the integral sense of the constant function 1. So that's something that's really useful to think about. The Fourier transform of the constant function 1 is the delta function. However, we're gonna use this in the next section to compute Fourier transform. So that's kind of why the delta function is important. It's a really short class today because of that. This is just something to get used to. What you should memorize possibly for your homework and for the future times is this, which you can also think about the inner product of f with the delta function shifted by x0 is going to be at x0. That's the one thing you should memorize from this section. I'm going to share another video that'll make the delta function a little clearer as well. Anyway, that's all I have. Thanks.